Hi, everyone. This is ME 5390, Advanced Thermal Design. We have a quiz. I'm gonna announce the quiz. Quiz number 1. Monday, 2/13, 4/26 p.m. as scheduled. Okay. This is important, so you have to prepare. I picked some of I think you have to at least go over the homework problem and some additional problem. You can study I think these are the homework, and this is some additional. Today, I'm going to go over some homework problem. Okay, I picked the problem. I'm going to go over today. Well, I don't have to, but we had not enough time to discuss the homework in detail. So I think I'd like to share with you homework solution problem. Before we start, do you have any question about the quiz? Open. Note. So you can look up any note.
Hey, Professor.
Yes.
On the Dropbox, it says the homework got changed from 7 o'clock to 4 o'clock.
Yes.
Within the past hour. Is it still 7 o'clock?
Yeah,
it's been 7 o'clock for a week now.
Really? From week now to
Yeah.
net? What is
I just turned in my last homework problem because I noticed it changed back to 4 o'clock.
February 6th is today due.
Yeah, but it said 7 o'clock. It was
It was at 7 o'clock for a while, so I
Okay.
assumed it was at 7.
No problem. You can upload anytime. Okay.
Okay, thank you.
So no problem. The late, I will not count on the late for that. You can, but you have to upload. Okay. That's no problem. Yeah. And I'm really sorry. I'm not a good grading, but I'm gonna post so at least you can look up the solution, even though gradings are late. Somehow the school does not provide a grader. I have two intensive graduate school. They don't provide. Please understand, I'm struggling grading. Uh, so I'm thinking I'm going to put less effort on homework. Although you are wrong, I don't have much time to correct it. So maybe I can give you some credit, but I will look at it. But I'm sorry, I'm not good in grading homework, but I will look at the quiz. Do you understand? So quiz is important. That's a evaluation, not the homework. I'm going to give you credit mostly. But quiz, I'm going to focus on. I'm sorry, that's my intention. Do you understand? So that's the a little bit change. But you're okay as long as I give you more credit on homework. You are going diligent, okay, you will have. But if you are not, nobody knows you are bad until you have quiz. That's the what happened. Okay. So anyhow, I'm focusing on the homework problem anyhow and on quiz. Any other question? Okay. Uh, um, you do not have a homework for this 1.1, but well, it's pretty simple concept. So I'm gonna discuss this homework problem. It's a mostly concept, nothing calculation. So an inventor claims to have developed heat engine that receives 700 kilojoule. I think I like to some important heat engine, 700 kilojoule absorb heat from source of 500 and produces network 300 kilojoule for certain time. So heat is joule is heat. So while rejecting waste heat to heat sink is 290. So high source, low source. Is it possible? Reasonable claim. Provide energy flow. Okay. So, how we can possible or not possible? Okay. So, let's say high temperature source at TH is 500 K, and raw temperature sink TL is 290 K. So obviously high source, so we can have a heat engine and produce some receive and reject and work, not really rate. Some network was given 500, 700. No, QH is receives 700 kilojoule. And network kilojoule. Rejecting, yeah, 209 QL, I don't know, but is this possible? So how we can discuss possible? Anyone? Any idea? Give me some idea. No numbers. How we can approach? Hmm?
Professor, I would say if the efficiency, you can calculate that, and if it comes out over 100, then it's not possible.
That is not enough. Yes, you're right, but that's not enough. If less than 100, then you would say okay. No, I don't think so.
Less than Carnot efficiency, just compare them.
Good. Thank you so much. We know how to compute the kernel, so it cannot be higher than kernel. Kernel is a so ideal, highest possible efficiency. That's the idea. Okay. So kernel we may calculate from this. Okay, that's the idea. And then this one has a efficiency, thermal efficiency. We can look up. Okay, then kernel, and maybe you can look at it. Okay. Question. So what is efficiency, thermal efficiency of heat engine is simple. I said the input output So anyone figure out it's quite simple. What would be input and output? What is
Input be your 700 kilojoules and your output be your 300.
So what is the input?
Input would be your QH, so 700 kilojoules.
Yeah, yes. Input must be heat. Output?
That would be your net work, so 300 kilojoules.
Yes. That's the efficiency. So 700 kilojoule over 300 kilojoule. That efficiency is 0.428. What is the efficiency of this in percentage?
$42.8.
Yes. Okay, let's see Cardinal. Is it possible or not possible? So what is a Cardinal? What is a cycle result gives us? Anyone? Some equations, Cardinal. That's what I asked actually. Is most important relationship. No one? Do you know that?
Isn't it 1 minus T low over TI?
I cannot. You said T L over T. No. T L over TH. Is that the Carnot cycle? I don't know. You have to complete your. This is so important, as a science, not only engineer. If you don't know this, you are not qualified any engineering, chemical engineering, mechanical engineering, electrical engineering. Carnot is important. That's what I'm saying. What is the Carnot cycle? The resultant equation.
Thermal efficiency equal to 1 minus TL by TH.
Say again. With slow. Say slow.
Thermal efficiency equal to 1 minus TL by TH.
Carnot efficiency 1 minus
TL by TH.
Yes. Or anyone else?
Or 1 minus.
No. I think yes, you're right, but I think it's more conceptually same, but the
Or
relation
QH over QL
equal what?
equals TH over TL.
Oh my goodness, even worse. Anyone?
1 minus thermal efficiency.
No. I'm talking about the QL over QH.
Well, it's TL over TH.
Yes.
I said QH over QL. So either way, it's the same.
Yeah. Anyhow, yeah, either way, yeah. So this is okay, but the more important is this. Okay, so that's the QC now. Thermal efficiency is QH over net. So if you look at, you can take a control volume here, engine. So first law, what is the first law is energy balance. First law, energy balance. So energy balance, QH, control volume, is a plus or minus into the engine.
Plus into the engine.
Plus or minus?
Plus.
Yes, thank you. QL, plus or minus?
Minus.
W, plus or minus?
Minus.
Yeah, equal what? Anyone knows? That's the first law. Equal what?
0, or if it's steady state.
Yes, because of steady state, no stored energy. So it's 0. That's why work net is QH minus QL. So now work is QH minus QL over QH is nothing more than 1 minus QL over QH. So can you calculate this? Do we know the QH, QL? No, we know this efficiency. So Carnot efficiency, Carnot is TL minus TH. Okay, so if you calculate 1 minus 290K over 500K, it's come up with
0.42.
0.42. So this is 42%. So now, is it possible or impossible?
Impossible.
Because the claim is greater than Carnot. Okay, once it's Carnot, I can switch to TL. So answer is impossible. We don't need to thousands of the detailed design or report. No need. No need to read it. It's impossible. You see? Is it? They have 1,000 pages of report. Pages. No need to read it even. There's something wrong. That's a very important concept. Thermodynamics. This you can apply to refrigerator. Same. Heat pump, refrigerator. Same. Okay. Now, what is a 1.9 is something like that. There is a plate. T1, T2. T2 is known. Okay, you can read it. The thickness is 20. Thermal conductivity 3. And area is 1 square meter. Emissivity, we don't know usually, but it was given. Emissivity 0.8. And ambient, even convection coefficient is given. And the surrounding is minus 10. Surrounding is depend on the, you know, location. If you stand cool night on the sky is surrounding. If you are in the house, the surrounding is ceiling, wall, or surrounding. So surrounding is whatever covers you. Okay. So -10, this is so cold. It will affect radiation. The homeless people sitting on the bench, there is a night, sky, cold, -10 degrees C. What would be a heat? That's the sky. But this guy is so smart. He covered the newspaper. So what would be surrounding is a newspaper, not the sky. It's a big difference. Anyhow, so here the question is, what is the question? I forgot. Determined. What is a T1? Determine the T1. So I would say I set the control value at the surface. No volume. Control volume at surface, no volume. And then heat balance, first law. Okay. So once it's control volume, surface, control volume, no volume actually. So what is the left side is the area is so flux, I can say that conduction. What is the heat mechanism at the outside is convection. The other is Q radiation. That's it. That's 3. Flux, since A is the same everywhere, you can say. So heat balance, Q conduction is a sign is plus or minus. This is control value. Say something.
Plus.
Yeah, first law. I said discuss the sign of first law. And then Q convection. What is the sign?
Minus.
Because depend on your direction. You direct it out. If somebody opposite is a plus, so minus. What is the Q radiation?
Minus.
Minus. Equal what?
0.
0 again. Why?
Because energy in is the same as energy out.
No,
We're not
no,
losing energy.
no, that's not enough. Wow, why is 0? It cannot be the same sometimes.
Steady state.
Steady state. We assume steady state. Student, do you understand? There might be some stored energy for certain time, short time. So that's not the correct answer. Correct answer is a steady state, which means in and out balanced, no stored. Okay. Now I asked the equation, but many students, they didn't provide. Anyone, can you figure out the conduction? Just the fundamental equation. I think we have your coordinate x, but tell me,
It's the flux, so there's no area, so it's K dt dx.
anyone correct this?
Or negative K.
Minus Ka dt dx.
Yes, because we have coordinate and vector heat is a vector, so we have sign. Because temperature, the flow is minus high to low. Okay, now anyone convection, do you have an equation?
That's H uh Ts minus T ambient.
Because this is a TS, whatever, and this is ambient. Because I directed the convection from surface to ambient. That's why S, you have to follow this is so important direction. Anyone, radiation, do you have any equation?
It's sigma emissivity times T T surrounding to the fourth minus T surface to the fourth.
Somebody else.
Or T surface to the fourth minus T surrounding to the fourth.
Why? Do you know why? Do you know why?
It's the direction. I'm sorry. It goes
Yeah,
from
yeah,
surface
yeah.
to surrounding.
Yeah, that's the direction surface to surrounding. Okay, that's why we have to use equal what? 0. So the problem is this conduction, the plate, steady state plate is the same as um, here is a T2, T1. This is T1. This is T2. So the TDX is mathematically further one first without the noting. So further one T2 minus T1. dx is the length, thickness for steady plate. So T2 is a TS, actually. We are using TS here. T1 is a question. So TS is known. TS is known. Do you think you can compute the T1? Yes or no?
Yes.
One more.
Yes.
Okay, that's it. So, but this including all the sign convention, very okay. So the sign convention. So, do you have any question about this problem? Okay. Let's move on. I like to have a break today, very early. I'll be back in 10 minutes. Okay, I will see you in 10 minutes. I'm back. I want to discuss the 2.9 heat sink natural convection. It could be forced convection, but this one is a natural convection, no forced, just a quiescent air. But since the heat sink is hot, plate is hot, there might be induced flow. So natural convection taking place, and we estimate convection coefficient, and we design. Okay, but you have to realize there would be possible maximum optimum design without constraint, no constraint. And usually that turns out to be too big. So some constraint, engineering constraint, maybe profile length too large for the device or whatever constraint, heat transfer. We don't need a very high heat transfer. We need a certain amount of heat transfer, then optimize something constrained. So if you look carefully at the book, two-way look at optimum design with, without constraints. Okay, so might be equations might be slightly different. Anyhow, so heat sink 15 by 12 centimeter W width and length. Vertical, as you shown, vertical plate is passively cooled, which means no fans. Okay, by natural convection using multiple phenol array, something like that. Ambient air is 30, so I think instead of W, I usually subscribe so that avoid the conflict in Mescat. We are not using Mescat, but I'm just accustomed. So in Mescat, W is what? So I cannot define W. It's conflict. So I use a subscribe. It's a good idea whenever we program. So that 15 centimeter length is again, Mescat is a liter. So I like to use subscribe. You can raise a question, students, any question, okay? Problem discussion, you might have some question, is 12 centimeter, okay? And I used to say base temperature, also I use V, ambient. Ambient is 30, and the base temperature is 85, something like that. So usually we need the difference is TB minus infinity is about 55. Once you subtract, it can be a K or C. Do you know that? Same. Yes or no? Yes or no?
Yes.
One more.
Yes.
Yes.
You should know that, okay? Don't confuse. Because 273 is subtracted. That's why I'm saying. it can be, the difference when you talk about is weird, but the same. And then they are saying the aluminum, because we have aluminum and other density air, so 27 kilogram cube. And K aluminum is 130 watt meter K. Okay, so we have to define it. And then T film, because the air property is not the base, not ambient. So 85, 30 divided by 2, and convert the K, something like that, because we need to look at the property of air. Table A2. And I got the K air at the film is, you just have to read it on 0 to a watt K, and kinematic is 1995 and to the 6, and alpha thermal diffusivity 27.8 and to the 6, and beta is expansion coefficient is T infinity. So you have to use Kelvin 134.5 K is whatever. Yeah, you can get it. Anything wrong?
I got a quick question for you, Professor.
Yeah.
On the quiz, are you expecting us to interpolate, or can we just pick the closest table value?
Say again?
On the quiz we have on next Monday,
Yeah.
do you want us to take the exact value, like interpolate the tables,
No,
or can we
no,
just
you have
take the
to
closest?
you have to look at the table. Why are you saying?
Right, but if we don't have the exact, like if 345 is not a measurement, they don't have it for 345. Maybe they have it for 350.
Well, then what can you do?
Do you want us to interpolate, or do you want us to just take 350 and call it close enough?
That's, you have to take care of it. Okay. So in order to 345 interpolation, and it takes time. You take all the time is a time limit, 2-hour exam. Are you gonna do it, or are you gonna use approximate? There is about 350K value. Are you gonna you approximate it? Which way?
Approximate.
Yeah. The property is a very weak function of temperature. So whatever if there is a 330K, I'm fine. Don't do that. Okay, spending time. Any other? I think you have to find something wrong. I did wrong. You have to find it.
Temperature is wrong. It's not 345, it's 330.5.
Say again.
Temperature at 345 Kelvin is wrong. It's 330.5 Kelvin.
I set whatever close, I don't know, whatever. Okay, this is not the big deal.
Okay.
Yeah, closest one use it.
Are the table properties supposed to be 10 to the negative sixth?
Thank you. This is a terrible mistake. This one is the same. Okay, don't make mistake. I really hate you mistake this reading the table. You know, if you mistake, the huge disaster all of your calculation is a disaster because of that. What happened is if you look at the table, there is a 10 to the 6, and then there is a number, temperature, 350, all kind of temperature, maybe 1995. That's what I had here. But here is 10 to the 6. So what happened is V times 10 to the 6 is 1995. So property is 1995, 10 to the minus 6, whatever unit. Say yes if you understand. Don't make a mistake. Don't make me, upset.
Yes, I understand.
Yeah. And what happened is not only this book, most of engineering thermodynamics, they use the same. So this mistake is terrible mistake. You can mistake at home. I know you can mistake at the school. I know you will mistake after school. Industry, you will mistake it. So this is a really bad situation. Everybody should realize what's going on and correctly reading since then. Not only this, every table appendix, not 100%. I found about 5% they use the opposite. So you have to figure out -6. Okay. So we have a property, and then you have to calculate what we need is optimum spacing. Is you can find the equations in the book. Rayleigh minus 1/4. So you need a Rayleigh, and then you can figure out about this configuration. Am I right? Okay, so I have to look at Rayleigh definition, beta V, my book, LB cube over alpha and the viscosity. So you can just use property and you can calculate it turns out 4.7, 10 to the 6, whatever. So you can plug in, and the optimum is 4.7, 10 to the 6 times about 8.7, a little. And then LV is, what is the LV? Length is 13, 12, 12. Be careful. You have to 12 times 10 to the minus 2 meter, because the, yeah. And then 6.9, 10 to the minus 3 meters. So 6.9 millimeter turned out about. That's the good spacing for optimal free convection. Okay. Now, the idea, I will tell you. The rectangle, this is first of all, rectangle, we understand. Multiple, we understand. But the optimum of a heat sink multiple will be very close to single fin. I told you, not exactly the same, but so I will accept if you optimize single fin and then assuming multiple fin calculate, I would accept it because it's a 1%, 2% maybe. But for the exam, it's fine. Do you understand? So once you single fin optimum, fine. You know how to single fin optimum. Okay, I think what is do you remember I don't want to show you, but
So you're saying for single fin optimum, you can use what for the exam?
say again.
What were you just saying about using it for the exam? It's fine within 1% for the single fin optimum?
No, I wouldn't say that. I need to find out the multiple fin.
Yeah, for multiple fin?
Okay, then what you gonna do?
We use are you talking about efficiency?
Everything, optimum, dimensions, profile, thickness.
Well, can't you use Z optimum equals the thickness?
That's what, yes or no. That's very dangerous. So you have to understand that's okay, but very dangerous. I will tell you why it's dangerous. But the concept is what is how to optimize multiple fin dimensions. You tell me. You tell me. What did I say? I said something. No one catch?
Well, I was asking you to clarify because I didn't quite understand what you said.
Well, then other students. Anyone understand that? How we can handle multiple fin, knowing single fin information.
Can you just find the number of fins and well, find single fin efficiency and then you multiply it by the number of fins, or the single fin efficiency is very close to the
Close, but still, I don't think you can get the, because you have to figure out multiple fin. Even you cannot calculate the number of fin unless you have a thickness and profile length. So
is profile length given though?
no, not
Or no,
given.
W is given. Well, number of fins I thought is W over T plus Z. And we can assume that T equals Z.
That's why.
For free convection only though.
That's why I hate to use equal, that equal.
It's approximately.
I made a mistake in my book. Yeah, that's true, but I didn't put it so that student would not know that. But still, you can do it. That's my mistake. I put it there, and every students they love to use it by mistakenly. That's what I'm telling you now.
Okay, so don't use that.
I suggest don't use it. Then what?
We would use this efficiency chart then for single fin efficiency.
Yes, you answered. Single fin efficiency. You answered already now. Look at the single fin. I said is very close to multiple fin optimal. So once you have a look at the, you know how to get the single fin efficiency, single fin dimension, single fin thickness, everything you can do it. Okay, then apply to multiple fin and design it. Then 1 or 2% error. I would love it. This is a rectangular. I think you have drawing 2.5 figure. Okay. So what is required is U. Once you have U value, once you have U value, this is U, but you need a HLK. Then once you have U value, you will see optimum, yes or no? You know that. Say yes. Once you have U, you have optimum. Right? Do you know that this is single fin?
Yes.
So once you have U value, you have immediate Q and V, and then you have some idea how to get it. Okay. Then constraint even okay, but without the constraint, you have to still, with the constraint is much easier because with the constraint, some volume is given, immediately you get the T. Once your volume is given, you get the T because V, small v is known, Q is known. If you know the heat transfer is given, immediately you can get some information, T, APL. So with the constraint is the easy part for you. So no constraint, then how to get the optimum? That's my question. I think.
Would
Okay.
we assume and then validate?
No, that is very difficult. If here assume validate. Okay. That is tough. If you figure out that, you are excellent. I'm not gonna tell you even now. With the constraint, fine. Without the constraint, you have a difficulty. But the book says this is a problem. I should not for without the constraint. Answer is without the constraint. Without the constraint, it is what was the thickness? That that was given in the book. Without the constraint, only free convection. Only free convection. So this is free convection. Then students use it. Everybody happy. But with the constraint is different story. You have to then you have to look up the numbers and you can design it. But I mean, this I said this is terrible. No, it's good, but I don't want to too easy for students. Still, you can look up the optimum design. Anyone students knows this how to get it? I don't think so, but
So without constraints,
yeah, how we
do
can
we,
get it?
so we still don't use the z equals t for without constraints.
Say again, G equal what?
The z optimum equals the thickness. We do not
Yeah,
use that.
I don't want to use it. If you use it, it turns out correct. But suppose you are not using that, then how we can figure out pre-convection or forced convection? Same problem. If it is forced convection, you cannot use GTT even. Am I right? This is only free convection. So if I make a if I make a problem forced convection, you have to figure out. You cannot use the GT optimum T. That's why I hate I provided this in the book. So mistakenly students use it, make it easy, but that's not the correct. Even
But you're
either,
saying we know you.
yeah, say we know you. Actually, we have to figure out the age. We have to figure out age, then we know you. Yes.
Right. So then we could take the peak at you.
Yeah.
And
Once
that'll,
you have U, you have a Q and the V. Fine. But still T and B is not known. What is the AP? AP is B times T.
times t.
Yeah. So AP is B times T. Still, there are BT, there is a BT. How we can figure out the BT?
Isn't APL volume?
APL volume, so you can plug in volume, but still T, yes, is not known. So still T here. QF is not known. Q is known, but QF is not known, actual. So how you can handle that? Is there any idea of QF? Any idea QF? Or expression? Yes or no? Somebody say answer. Is there any expression for
Would we have to do a system of equations?
what is that?
Would we have to do two equations with two unknowns and then solve for those?
You cannot. If two unknowns, you cannot. That's why you have to eliminate one. Even QF is not known. Okay, now let me clear. For problem, what is the problem number of this? Again, 2.9. No problem. Okay, there is an example problem for maximum, optimum. Without the constraint, fine, because you want to use this. And with the constraint, fine, you're gonna somehow figure out it much easier. So you solve it. That's the example problem. Shows you. But probably I can change problem to forced convection. Then you have a big problem. You cannot use these. Do you understand or not?
I understand, but I don't know how to do it.
I don't
mean,
know. I'm not gonna tell you. You have to figure out.
Then how are we supposed to learn?
Well, you have to figure out. If I give you now, it's easy. Everybody, okay. No, don't think about it. Okay, now,
Are
H.
we gonna find out before the exam?
I don't know. I will think about it. Now, first you have to figure out H. Okay, H. How to figure out the H even is not easy. What is the idea of H for this kind of configuration? Then you have to look up. There's a couple of problems. Anyone? What we have to look up in order to have a H? Some name.
That's the Nasalt and the EL one?
Yes. LM bar.
Ellen bar, thank you.
Yeah, LN. What is it? Yeah, bars. LN bars. Once you LN bars idea, then follow LN bar. Why? Because he provided the equation. I don't know. He provided, so I follow. That's it. For two vertical flow condition, two vertical plate flow. That's the LM bar. Once you have that, then you can get the H. So you have a H, then same again. You have a H, then you have U. So with the constraint, you can get it. Without the constraint, problem. For free convection, maybe you can use, nobody can claim it because that was true. But forced convection, you have a problem. Big problem. You cannot use this. G optimum is T. Then how you can get the without the constraint? I hope you get the point. And that's a small part of the quiz actually. So even without knowing this, you can get others and you can get 90. I'm fine, but I like to know somebody who are the best. I like to move on. What is what is, I like the 3.4. 3.4 is very, I don't want to read it. This is heat pipe.
Professor,
Yes.
does it have to do with beta being optimum? And we can find
No.
MB from that or no?
No, that's not,
Okay.
that's not what I do. Okay. I do a hint. I do is I try to figure out these QF different expression. Then try to solve it. Okay, because QF is not known, but the expression of heat transfer in terms of T and B, so that maybe I can figure out. Okay. Okay, now. Well, without that, you can be still A students. I really know who are the best. Sorry, I want to know. So this one is a very similar heat pipe. First of all, we know how to handle heat pipe, evaporator, and condenser. All equations I can handle. And here, this is nothing more than you understand H E, okay, E, say evaporator, and yes or no? Do you understand this? Heat sink, efficiency, fin efficiency, HA.
Yeah.
And this is efficiency overall condenser, H condenser, A condenser. So two, I said this is the same size, so it's very similar or same. One, if you figure out this, so how to figure out the overall efficiency? Do you think you can figure out once you optimize it? Optimize first. What is the idea of optimization with the constraint? There was a sequence was given. What is the idea of a constraint? The optimum with the constraint of sequence? You know that how to do it. Say yes. If you able to figure out the optimum design. Multiple fin.
Would W be equal to the LE and LC?
What is the W?
I'm talking for the multi-fin. That's
Yeah, multiple fin. Yes.
so your W would be equal to the LC or LE?
W is the width.
Yeah, the width of the whole thing.
The whole. No,
No, I'm
you can
talking for
separate
the
about the
fin
evaporator.
area. For the fin area. Because I was just this is the homework problem 3.4, right?
Yeah.
Okay. I was just confirming like W for the condenser is equal to LC.
Yes. Yes. You're right. Yeah. Yeah. That you have to figure out that. So the idea now, don't detail. Do you think you can optimize this multiple fin? Yes or no?
Yes.
Yes.
What is the idea? Give me a little describe. Multiple fin.
Well, it doesn't as the problem statement gives you the well, you assume L
No,
to
no. More conceptual answer, not detail. Multiple fin, how you can optimize it?
Optimize a single fin?
Yes, thank you. Again, it's not exact, okay? It's a little bit more than the single fin, but I said the 1 or 2%, who knows? But I will accept if you single fin look at it, design, R2, thickness, and then multiple fin, we need a space, okay? And you have to figure out the age, whatever. You can use a chart. You don't have to look at the Bessel function. No, chart, optimize. So you're able to optimize. Answer is yes. Once you optimize, this is the same. And then all you need is a heat pipe. And then what you can do is heat transfer from here. Look at it. I like to delete. I like to delete. No, too much. No. Ah, anyhow, yeah. Okay. Now, the Q and the Q and the Q is out. The same one Q. So when I look at Q is first the total heat sink and the heat pipe. This is a heat sink evaporator. And then another condenser. This is evaporator, heat sink. And temperature, T infinity C, T infinity E, Q. Can you say that? Yes or no?
Yes.
Yeah, you can say that. So do you know the thermal resistance of heat sink? Yes or no? Can you write? Heat sink, you have some knowledge of heat sink. What is the thermal resistance between temperature over here, base temperature, T base, pipe? What is the what is the heat sink thermal resistance? Oh my God, somebody has to answer. We studied for a month.
What, we studied the thermal resistance of the pipe. Are you talking about the natural log D out
No,
over
heat
D in?
sink. Just think about heat sink.
Or the 1 over H pi DOLE? Or D out, length of the evaporator?
1 over what?
H pi,
No. I'm not talking about that. Somebody. I think we
Question.
thermal resistance between this and TB here. TB is one temperature. TB between here evaporator and the TB.
We never really went over this. I was trying to contact you earlier about it.
But then you don't understand anything about the heat sink.
Well, this one doesn't have contact resistance, right?
No. There's no contact resistance. Zero. I'm just
Okay. So is it it's not the radial resistance or
I think the heat, if you don't, the heat sink we discussed, you have to know thermal resistance of heat sink. Oh my. Multiple or even in case of rectangular. T base and the fin. Well, what is the heat sink T infinity? The same. This is the same as a fin. Well, that's the problem. I think you don't understand anything about heat sink.
is it the L over KA?
This is a heat sink. This is a TB. This is T infinity. Flow. H, T infinity. So what is a heat transfer? Anyone?
The convection?
Give me some what is information is TB, T infinity, heat flow out, and what is the efficiency? Do you know efficiency of concept?
Yeah.
What is that?
Total over max.
Do you want the fin efficiency?
Fin efficiency, I'm talking about the fin efficiency.
The square root of HPK
Oh, no.
Or you want the
Overall. We talk
tangent,
about
hyperbolic tangent of MB over MB?
we talk about the overall.
Overall? That's Q total over theta B HAT, a total area.
Okay, single fin efficiency. Single fin. Do you know the single fin efficiency?
QF over HPB theta B.
Say again.
HPB theta B.
H area of the fin theta B.
Can you correct something? Can you correct this? HB what?
P.
HP what?
HPB.
HPB. Okay. Yes. Yes. Okay. So this is actually QF of Q max. So we know the max QPB. Yes. We know that.
Yes.
So single fin is a efficiency. Once you know the efficiency, then HPB zeta B. HPB is actually the total area. Total area. You get nothing more. Total area. HPB. Yes. Single fin or whatever multiple fin.
It's the area of the fin.
Yeah, area of a fin. That's a single fin. Yes. And then single fin is you can calculate the MB hyperbolic MB. You can even calculate, right? Or there's a many ways. There is a tables or chart. You can figure out once you figure out the single fin, then you can figure out the single fin heat transfer. Now, do you know overall? Or how you can figure out this overall? Okay, I would tell you some equation you can find. N, number of N, A of single fin, A of total, 1 minus single fin. So your information, number of fin, single fin, efficiency, total area, and single fin area, then you can overall. And then what is overall is Q total minus Q max. Anyone? What would be Q total over Q max? Anyone figure out? What is maximum heat sink? Because once you know the single fin, very easily you can figure out the total max single.
Would it just be a single fin times the number of fins?
No, that's a total.
It's the overall efficiency times,
No. H times what? Don't say P, okay? Instead of P, what can you do?
total area,
Yes. And then what?
theta B.
Yeah. So once you know overall efficiency, you can figure out the Q total. Okay, so what is the Q total? Is overall efficiency H A T zeta V. You can calculate, but you need the overall efficiency. In order to do that, you have to go. But the idea of this is a concept of overall is temperature difference of Q total. So what is the temperature difference is depend on, okay, overall for single fin is T B minus T infinity. This is just one side, evaporator, Q total evaporator, Q total evaporator. One side is TB. So now,
Would we assume the efficiency is the same on both sides then?
yeah, TB is the same. Actually, the heat sink, heat pipe, TB is the same everywhere.
So the efficiency, I'm saying, would be the same.
Yeah,
the
that's
condenser.
you can assume same. That's you can assume same. That's what I said. Same number of fin. Now, so what we can do here is 1 over efficiency evaporator H evaporator A evaporator. This is thermal resistance of heat pipe. This is 1 over efficiency overall condenser H condenser A condenser. So this is almost the same. This is the same efficiency H E A E is efficiency condenser HC AC because of given information, the same. So all you need is a resistance of heat pipe. Do you think you can calculate? Yes or no? Answer.
Yes.
What is that about? Can you tell me about the just the conceptual heat pipe?
That's
Simplest one.
the radial conduction resistance.
No. More conceptual.
It's, okay, it's the natural log of the outside over the inside diameter divided by.
No, not detail. Just the first concept. What you have to look at. Anyone? The 2 times of what?
That's if they're physically identical, you're saying? So it's 2 times the RPE plus RWE
Our pipe.
pipe evaporator
Yeah.
plus our wick evaporator.
Yes.
But is that only if they're the same
No.
length?
Yeah, 2 is the same. Yes. So yes. So once you figure out that, then you can. That is a resistance here.
Okay. So
So
by
what
physically
you can
identical,
do,
you just mean the same length, right?
yes, yes, yes. What you can do is finally the Q is if you resistance T, what is the starting point? T infinity E minus T infinity C is nothing more than resistance heat pipe 1 over overall C HC AC. So once you figure out this, you can get the total heat transfer. That's the problem. I think so. This is heat sink, radial heat sink, and the heat pipe problem. Any question? I'm done.
Are you just gonna post the exam on e-learning for us to take, or
Yeah,
is
I'm
there
going to
email?
post. I'm going to post.
Okay.
So you can look at it. Okay. Any question?
On the syllabus, it says the exam is 4 to 6:30, but earlier you said 4 to 6.
What did I say? Say again. Would you repeat your question again?
Earlier,
Oh,
the
4 to
beginning, you
6:30. Yeah, yeah.
okay.
I'm sorry. It's very confusing. 6:30, I will give you. So 2 hour, 30 minutes. Yes.
And then how many questions will we have?
No, I haven't decided, but
Okay.
something like that. Okay. I mentioned my concept of quiz. You know, any other question? Well, you think about it. Yeah, still we have time. Question.
Is it quiz or exam, or is it two different
It's
things?
a quiz. Quiz. Number 1,
Okay.
20%. Choose.
When it's horizontal, you have whatever gamma or whatever. Is that in radians or degrees if it's not horizontal?
It's a horizontal layout.
So it's always going to be horizontal?
Yes.
Okay, I just didn't know because we have to take cosine of the angle if that would be
It's a
radians or
horizontal.
degrees.
Horizontal.
Okay, thank you.
Any question? Yeah, still, you have question, still. Okay, yeah, good luck. And I'm, I'm not good, all right? Everyone knows. Okay, see you next hour. Bye.